go wrong in the economy or the meltdown that happened in 2007, no country was shielded. So that's a non-systemic risk. Even if I have 40,000 shares or 40,000 different portfolios, it's still the same problem. So it's kind of like a problem with the bond prices estimation of default intensity. So now, why are we doing this? The reason why we're doing this is two. One, if a company, a finance company, wants to give a loan to an individual, I need to know how much risk I'm taking on that individual. So I'm worried, I need to know how much, because the higher the risk I'm taking, I want to get more return. So if I'm going to do that, I should be able to analyze and have a model to know how risky this individual or this company is. So we use this situation, the one that we're going to talk about next, which is the net metal model, to first calculate interest rates. Secondly, to be able to know how soon this guy has a chance of defaulting, basically. And that will help me be able to project for the future. So now we've looked at default intensity from bond prices and historical data. Now, somebody now proposed something, because when you look at historical data, you have to rely on the credit rating companies to give you a rating before you can predict what a company is going to do. But what if I want to make a decision now? That's where Meton comes in. And he actually, because I can't rely on that credit rating companies because they give credit ratings every 6 months, then I have to create, the Meton had to create something. So he considered this in the case of the company. The value of the company as at today. He considered the value of the company at any time t, and all these other things that I listed here. But the main problem for him is that we can't get the value of the company as at today, and we can't get the volatility of an asset as at today. Now, the sigma E, which is the instantaneous volatility, we can estimate that from historical data. How do we do that? Yeah, we look at the trend for the past 50 years and we can say, okay, this is what usually happens. Every 10 years there's a meltdown, every 15 years it goes up again like that. So we can estimate that. But that volatility of an asset, we can't estimate. So those are the two problems that we have. Now, equity. What is an equity? I'll try to paint a scenario of what an equity is. An equity is, if I have a company, what the price is quoted today at $20, and the company has 100,000 shares. Now, how do I know the equity of that company? If I want to know the total value of that company, I multiply $20 by 100,000, and that's 2 million. So the company is worth 2 million, but the company holds 2. That's debt. So the debt, if I subtract the debt from the value of that company, I get the equity. And that's what the company is actually worth right now, basically. That's what the equity pricing is. So we're going to be doing a lot with the equity in this case. Now, in the stock market is really unpredictable. So because of the randomness, we're going to focus on stochastic differential equation. OD, it's kind of like creating a controlled environment. It's like working in a vacuum. But stochastic is more realistic. So that's what we're going to be doing. Now, before we introduce, before we can define stochastic process, we have a lot of definitions that we have to define. First, the random variable, the sigma algebra, everything is in the paper if you need to look at them. The random variable, sigma algebra, measurable space, probability space, complete probability space, measurable set, Borel set. We did all of that in real analysis. Borel sigma algebra, Borel measurable set, then you define the random variable, then you define the distribution, the expectation on a set, independence, which is basic independence in probabilities, then you can define the stochastic differential equation. Then, there are two types of stochastic differential equation. There's the continuous and the discrete time stochastic differential equation. The continuous time, the way it sounds, it's indexed by the continuous. It's indexed by the continuous. Then the discrete time is indexed by the discrete. Then we go on. We try to define the Brownian motion. The Brownian motion is a continuous stochastic process which satisfies the following conditions. I'm not going to go into that because of time. Then white noise. White noise is basically the time derivative of the Brownian motion, which is what I have here. That's the white noise. And going on, then I have the geometric Brownian motion. A geometric Brownian motion is a continuous stochastic process in which the logarithm of the random varying quantity follows a Brownian motion. And it has a drift, and it also has volatility. And this is basically what we're talking about. This is the drift, and this is the volatility. I'll define the drift and the volatility so you can follow. So if you apply Ito's lemma on an asset, and on an asset, the logarithm of an asset, you arrive at the geometric Brownian motion. But we'll explain that a little further later on. Then there's the variance. Variance is the measure of how far a set of numbers is spread out. Then there's the volatility, which is the square root of the variance. It's just standard deviation, the measure of risk, basically. And we have the drift, which is the return on an investment, basically. That's what the drift is. That will define the stochastic process and the stochastic integral, the Ito's process of the stochastic integral. Now, Ito's formula. The derivation is in the paper, but the difference between the Ito's formula and the regular calculus is this 1/2 second derivative of dt. That is the only thing that differentiates that derivative from the regular derivative we know from ordinary calculus. So going on, we have all these consequences from the Ito's lemma, which we're going to use a lot. dwt is the square root of dt, and dt squared equals to 0. Now, we go back to the value of an asset. Now, there's one thing I need to state here, which is this. It says, if the company asset, VT, is subject to a risk-free rate in the risk-neutral world, the one price derivative under the absence of arbitrage hypothesis. This is central. Now, what is the arbitrage hypothesis? The arbitrage hypothesis is kind of like there's no opportunity for you to take advantage or to have a leverage in any situation, basically. Like, okay, I know that the price of oil sells in London at $20 and it sells in America at $21, and I can take the difference. No, that is arbitrage. But in this case, if it's 20 in London and it's 20 in America, that's no arbitrage, and that's what we're going to be considering. So we'll go back to the geometric Brownian motion, which is what we have here. And if we now we'll pass and we'll try to derive the Black-Scholes formula. So to derive the Black-Scholes formula, we take the derivative of this ln and the ln function, and we'll find out if you take the integral and you take the proper exponent, you'll find out that Vt will give you this, which is the geometric Brownian motion. Now, in the Mertens model, a Mertens model is actually a call option on the asset. The equity is a call option on the asset. What is a call option? A call option is I agree with somebody today that I'm going to pay a price for an asset in the future, and I pay him a certain amount of money, $500. And I tell you, okay, I'm going to buy this thing for $5 million in the future, but take this $5, $50, this is your charge for the agreement between us. Now, if I invest that amount that I want to pay you in the future into kind of like anything, and we have a strike price for the future, and in the end, I get, instead of 1 million that I'm expecting, I get 900. I won't buy that option because it went lower. The only thing I will lose is the money I paid you. So it's either it is higher than 1 million. If it's like 1.1 million, then I buy it from you and sell at 1.1 million. Take the difference of 1 million and 100,000. That's my gain. That's kind of like what a call option is.
On the first formula there is a typo. It's not 0. It's capital D. On the ET, the formula, the top, on the right hand side, you have a 0.
Which one?
The first
This
formula,
one?
right? Like go to the
This
right.
one?
Oh, yeah. It's not zero on the
Okay.
right hand side.
Is D.
It's
This one, right?
That's D. Yeah.
Okay. Yeah. Because it's a difference. It's equity. It's the difference between the value of asset and the debt, basically. Sorry about that. I did this in a hurry yesterday.
Mhm.
So now we pass. If we do this, we pass and we try to compute E naught. What is E naught? So if I have a price in the future, I can discount it backwards. If I'm discounting, that means I'm multiplying by the E to the R to the T. So if I'm multiplying by this, I'm discounting to the present time. That's what it means. So I can discount backwards to 0. Now, I know this for sure that omega t is square root of t times x, which is kind of like the Gaussian. Then x is a Gaussian or a normal distribution with mean 0 and standard deviation 1. Okay, now we can derive this from the equation above. If we solve further, and we have that x is less than this because, starting from the geometric Brownian motion, we can solve for x. If we switch from this geometric Brownian motion, we can solve for x, where we know that omega t is that. If we put them in and we'll solve for x, we'll see that x is less than ln of d over that, which we're going to call negative d2 for now. Now back to the discounting equation. Now I'm discounting that equity, which is the difference between the value of the asset and the debt. And that's why I have this equation here. I'm discounting this equation, which is the difference between value of the asset and debt. So now if I look at the second integral, if I do some manipulations, I'll arrive at this, which is just that. Then the second part, which is the first part of the equation, if I complete the square on the exponent and I change the variables, then I'll find out that V naught minus ND1. And in the end, I'll find this equation. Why am I looking for this equation? Like I said earlier, our goal is to be able to estimate the volatility of the asset and also to be able to find V naught. So we need two equations to be able to find V naught. Now this value, n of negative d2, is very important for us because it's the risk neutral probability of the company to pay a debt. That's the probability of default, basically. So going on to the Black-Scholes formula, we can find a general formula for the Black-Scholes formula at any time t. The initial one was at time 0, t equals 0. So this is for the one at any time t. It's practically the same thing. So now, recall that we were doing, you recall that we need two things to solve. We need a second equation that we're going to solve simultaneously. Now we'll go to the initial equation again, and we'll take the geometric Brownian motion again. Then we'll take the partials, because this ET is just like VT2. It is a geometric Brownian motion. If you take the partial on it, we'll have the equation, the second equation. And this second equation, which is this, if we solve this second equation and the first equation simultaneously, we can find sigma V and V naught, which is what we need. Now, and then a good example to illustrate this is the one that I illustrated here. What is the goal of this example? The goal of this example in the end is to know what I will recover if there's any event of default. How much will I recover back? So now we'll set up the equation and we use, because this is computationally tedious, we use Excel solver and we found out from this example that V naught is 12.4 and sigma 0 is supposed to be sigma V. Sorry. Sigma V is actually 0.2123. And in the end, if I put this D2 that I found out, if I put it into the normal equation, I'll find out that the probability of default is 12.7%. Now, the market value of debt